In this session, we're going to perform operations with functions. Turns out we can add, subtract, multiply, and divide functions just like we can real numbers and algebraic expressions. And sometimes our answers will be numbers, and sometimes they'll be expressions, depending on what we're being asked to find. In our first example, we're given two functions, f of x equals 2x plus 3, and g of x equals x squared plus 4x minus 1. We're asked to find f times g of 2. I want to talk about the notation just for a bit. We're using a dot to represent the multiplication of f and g. And we need to make sure that we don't ever write an open circle in this context, because that actually is going to have a different meaning, and you're going to see that in a different session. Finding f times g of 2 is the same thing as finding f of 2 times g of 2. In other words, we need to find out what each of these functions is when x is equal to 2, and then multiply the products together. As I'm sure you can confirm, f of 2 is equal to 7, and g of 2 is equal to 11. Therefore, f of 2 times g of 2 is going to equal the product of 7 and 11 for a result of 77. Yep, it's that straightforward for that one. In part B, we're asked to find f times g of x. Notice that we aren't being asked for a particular value here. We're asked for f times g of x, which means we're supposed to give a rule for f times g, an expression, if you will. As before, f times g of x indicates f of x times g of x. In other words, we aren't being asked to use a number, we're being asked to multiply together the expressions that define each of these functions. And so, f is 2x plus 3, and g is x squared plus 4x minus 1. And we're going to multiply together these two expressions. And when we do, we're going to get 2x cubed plus 11x squared plus 10x minus 3. And that's the expression represented by f times g of x. Next, we're asked for f plus g of 4. Using what you know, I'd like for you to compute that. Pause the video. F plus g of 4 is the same thing as f of 4 plus g of 4. And so we need the values of f of 4 and g of 4, which I'm sure you just computed and found that f of 4 is equal to 11 and g of 4 is equal to 31. And so adding these together, 11 plus 31 is going to give us the answer that we're looking for, which in this case is 42. Next, we're asked for f minus g of x. And as I'm sure you've concluded, what this means is the expression that defines f, 2x plus 3, is going to be the first term, and then we're going to subtract x squared plus 4x minus 1, the expression that defines g. I've put 2x plus 3 f of x in parentheses, even though I didn't need to, just to say that that's the first function. However, g of x, because it has more than one term, and we are subtracting, does need to be in parentheses. So after distributing the minus sign and putting our answer in descending order, we're going to get negative x squared minus 2x plus 4 for an answer for f minus g of x. The domains for each of these, the two that we have found with an argument of x, is the same as the domains of the original functions. In other words, these have domains of all real numbers. The things that we need to watch out for regarding domains just aren't present in these expressions. However, in part E, we're asked for g divided by f of x and its domain. Well, g divided by f of x is the same thing as g of x divided by f of x. And so is going to be x squared plus 4x minus 1 divided by 2x plus 3. In this context, you'll be relieved to know we don't have to perform polynomial division or anything like that. And in fact, this is going to be our final answer for g divided by f of x. But we were also asked for its domain. When we consider the domain of a function like this, or domains in general, we need to make sure that the denominator does not equal 0. So in this case, we need values that do not make f equal to 0. So since f is 2x plus 3, the domain of this function is going to be the set of x such that x does not equal negative 3 halves. Remember, that's the value that would make f equal to 0. Next, we're given another pair of functions. F of x is equal to x squared plus 8x plus 15, and g of x is equal to x plus 3. We're asked to find f divided by g of x, f divided by g of x and its domain. As before, this is just going to be a quotient of the functions, so giving it the same kind of color coordination and writing this down as the same in the same way we did before. F divided by g of x is the same thing as f of x divided by g of x. We have to note, though, as before, the denominator function, in this case g of x, cannot equal 0. When we first write down the expression, we're going to write it down as x squared plus 8x plus 15 divided by x plus 3. If it looks like this is something we might want to simplify, you're absolutely right. It is. We're supposed to simplify expressions when we can. And in this case, what that means is the numerator is going to factor into x plus 3 times x plus 5. And the denominator is simply x plus 3. And so we can divide out that common factor of x plus 3 in the numerator and denominator. And we might be tempted to say, hey, this quotient function is equal to x plus 5, and be done with it. But we'd be wrong. Reason being, x plus 3 is not supposed to equal 0. Therefore, x cannot equal negative 3. If you were walking down the street and you encountered this expression, x plus 5, first I'd wonder where you are. But then if you were asked, hey, what's the domain of that expression, you'd be saying all real numbers, I'm sure. In particular, if somebody asked, can I put negative 3 in place of x for the expression x plus 5? You'd say yes, and you'd be right. But we have to remember our roots. Remember where this expression came from. This came from the quotient of two functions. And in that consideration, x cannot be negative 3. And so even though it looks like the problem where x is negative 3 went away, we have to retain the restriction. In other words, let me get some room to write what I'm going to write. In other words, f divided by g of x is equal to x plus 5, provided that x does not equal negative 3. Now, to answer this in the format in which it was asked, I'd say f divided by g of x is equal to x plus 5, and that the domain is the set of x such that x does not equal negative 3. That's the complete answer to the question, and the point of this exercise is really that domain restrictions that look like they go away don't actually go away. The next example illustrates how we can write down formally what the domain of a combination of functions is. Here we're given, again, two functions. F of x is equal to the square root of x plus 5, and g of x is equal to the square root of 3 minus x. let's consider the domains of f and g. The domain of f is the set of x such that x is greater than or equal to -5. Or, if you like, square bracket -5 comma infinity parenthesis, right, in interval notation. And the domain of g is the set of x such that x is less than or equal to 3. In interval notation, that's going to be -infinity to 3 with, again, a square bracket at 3. If we picture this on a number line, then the interval for the domain of f would be a square bracket at -5 and shaded to the right. And that for g would be a square bracket at 3 shaded to the left. The domain of f plus g, and by the way we would write f plus g of x, I know it's not what we're asked for, but I still want to show you, is simply the square root of x plus 5 plus the square root of 3 minus x. And because we don't have like radicals, I can't simplify that any. So that's just kind of a note for your edification. If I'm going to evaluate f plus g at a particular x value, though, it's got to be a number that I can put into f and a number that I can put into g. In other words, where we see the interval, it's the overlap. It's the numbers between -5 and 3, including -5 and 3 themselves. Therefore, the domain is square bracket -5 comma 3 square bracket. It's what we call the intersection of the intervals that give the domain of f and the domain of g. In symbols, this interval is the domain of f upside down u. That's an intersection symbol. Domain of g. An intersection indicates overlap. And so if this were, say, what we call a Venn diagram, where I have the domain of f represented by some set and the domain of g likewise represented, kind of like a MasterCard logo, the domain that we were just talking about is the set of numbers that exists in both domains. Things change up just a little bit for f divided by g. First off, f over g, even though we weren't asked for it, of x is equal to the square root of x plus 5 divided by the square root of 3 minus x, as before, just putting together the two radical expressions. However, if I'm going to evaluate some number for f divided by g, then I need to be able to put that number into the radical for f as well as the radical for g. The one additional consideration we need to make is that because it's in the denominator, the square root of 3 minus x cannot equal 0. Therefore, x cannot equal 3. So this domain is going to be a square bracket at -5 because the numerator can equal 0, comma 3, but at 3 we have a parenthesis. So this is the domain of this quotient function. Ultimately, the domain of something like f divided by g is going to be the intersection of the domains of f and g, with the added bonus that g of x cannot be 0 because it's in a denominator.